Hey everyone, so we're going to be doing some more LeetCode today, and today we're going to be doing problem number 52 on LeetCode and Queens 2. And this is a hard problem, and it's a good example of a backtracking problem, which is an algorithm that you're going to want to know for coding interviews. So let's take a read. So the n queens puzzle is the problem placing n queens on an n by n chessboard such that no two queens attack each other. Given an integer n, return the number of distinct solutions to the n queens puzzle. And we can see, if you know how to play chess, the rule for a queen attacking is a queen can attack down, it can attack left or right, and it can also attack both diagonals. So this queen can attack this way and this queen can attack this way. And so you can see that in both of these solutions, none of these queens can attack each other in any of these ways. So let's take a look and let's figure out how we can do this and how we can come up with these solutions. So let's just take this 4x4 board. Also, a nice hint that I found to know that it's going to be backtracking instead of some dynamic programming or things like that is when you look at the constraints, typically for backtracking, because you're not doing any kind of minimization, you're doing all the solutions possible, this constraint, this n, or whatever you're going to be iterating through is usually going to be pretty small. Because once it gets big enough, if you're not recording anything you're doing, it's just going to take too long. And so when we're replacing these queens, let's just go through this example. So we're going to be iterating row by row and trying to place queens, and we're going to try to get every possible solution. So we're going to start at, let's say these rows are 0 indexed. 3, 0, 1, 2, 3. We're going to start at the first row, and we're going to try to place a queen. So at the first available index that it's valid, which means the square isn't being attacked. So let's just try to place a queen here. Now we know that we can't place another queen on the same row. So as soon as we place a queen, we can go to the next row. Now we try to place a queen at the first possible location, so we can't place one here because it would be attacked. Can't place one here, it would be attacked. So we try to place one here, go to the next row. Can't place one here, it would be attacked. And then all these three are attacked by this one. So as soon as we know we can't place it anywhere, now we recurse back to where we placed the last queen. We placed it here, so we're going to recurse back. We're going to remove it. We're going to put it here. Then we're going to go down the row again. Can't place it here. We can place it here. I'm going to go down, can't, and can't. Recurse back. Can't place a queen here, can't place a queen here. So then we're going to recurse back, delete this queen, recurse back, delete this queen. Now we try to place here, go down, can't. Place here. And this is a valid solution. And the way we're going to know if it's a valid solution is we're going to get to this row, we're going to place a queen, and as soon as we could place a queen on this bottom row, and we go to the next row, as soon as we get to a row that's out of bounds, that's when we know we have a valid solution, so we can increment our solution counter. So we're going to recurse again. Going to delete this queen. Can we place anywhere? Nope. Okay, go back. Place here. Can't. Place here. So this is another valid solution. Okay, so we're going to go back here. Okay, we're done with this. Done here. Can't. Go back here. Try to place here. I can't place here, so here. And then we can't place anywhere here, so we're going to go back. Place here. Can't. Go back. Can't. And then, now that we've tried to place everywhere on the row, on the top row, when we've recursed all the way down, we're done. So we found two valid solutions in this case, and that's what you can see. So there are a couple things that we need to know. First, how do we know if we can place a queen? So let's say we're at some index, like here. How do we know if this is a valid index that can't be attacked? So remember, a queen can attack up and down, so it can attack in the same column, it can attack in the same row, it can attack on both diagonals. Now, for the row, we don't need to check if we place the queen on the row because our algorithm is going to place queens one by one on the row. So it'll try to place it here. If it can, before it places it here, it'll remove it from here. So we don't need to check the row because our function will just place a queen one at a time on each index. Now for the column, we need to check, do we have a queen in this column. And then we also need to check the diagonal. So let's say we have this diagonal. Let's say we try to place a queen here. You need to check this whole diagonal and make sure, is a queen attacked? So what do these diagonals have in common with each other? Well, let's just try to think of, like, if this is the row and this is the column. Is there some way we could add up or subtract the row and the column to get this diagonal? Well, let's see. If this is 0, 0, this is 1, 1, this is 2, 2, this is 3, 3. So on this whole diagonal, the row, or the column minus the row equals 0. Right? So 0 minus 0 equals 0, 1 minus 1, 2 minus 2, 3 minus 3. Let's see if that's true for another diagonal. So let's try this one. So this is column 0. Sorry, column 1. Yeah, so this is actually column. This is row. Okay, so column 1 minus row 0, so that'd be 1. 2 minus 1, 1. 3 minus 2, 1. So it's true here as well. Let's try one more. 2 minus 0, 0, or 2. 3 minus 1 is 2. So we can see this left diagonal, column minus row, is always going to be the same value for the entire diagonal. So we could just say this left, we'll call this the left diagonal because it starts at the left, goes to the right. Left diagonal, column minus row is the same. Okay. Well, what about the right diagonal? So this diagonal right here. Okay, can we do anything here? So let's see. So this is row 0, column 3, row 1, column 3, row 2, column, or sorry, row 0, column 3, row 1, column 2, row 2, column 1, and row 3, column 0. Well, can we add them? Well, if we try to add them, this is 3. Or sorry, can we subtract them? So this is 3 minus 0, so it'll be 3. 2 minus 1, 1. 1 minus 2, negative 1. So we can't subtract. So let's try to add. Okay, 3 and 0 is 3. 2 and 1 is 3. 1 and 2 is 3. And 3 is 3. So when we added them, they were all the same. Let's try another diagonal. Same kind of way. So 2 and 0 is 2. 1 and 1 is 2. 0 and 2 is 2. Okay, so for the right diagonal, we know that column plus row is the same. So we can write that down. And so the way we check if our square is a fine square, we're going to have a dictionary for columns. We're going to have a dictionary of left diagonals, dictionary of right diagonals. And so we're going to check, is our box in any one of these? If it is in these, that means we can't place it and we go to the next one. And then for our value, so these are going to be the keys. For our value, we can just have a Boolean like true or false. So if there is something in here, we can say true. If there isn't something in there, we can say false. And so combining that together, our code is going to be start at this first row, try to place a queen. If you can place a queen, go to the next row, try to place a queen. If you can place a queen, go to, and so on. So at every row, we're going to try to place a queen at every single column. And then anytime we get past this n, we know that we have a valid solution. And then we just recurse back. So let's try to code that up. So we're going to need a dictionary for columns and the left and right diagonals. So let's do that. And I'm going to make this a default dict. And it's just going to be a Boolean value. So columns. And I like using default dicts usually because you don't need to check if something is in there. You can just look right away and there's a default value of false in there already. Okay, so now we're going to need also we don't need an output variable because in our backtrack function we will directly handle that. So if let's say we have this backtrack function, we are just going to add 1 every time we recurse down and there's a valid solution. So we can try every single backtrack function and then we just keep adding 1 when there's a valid solution, and then so we should return the total, which will be our output. So let's define that. It's going to take a row starting at row 0. Remember, we're going to go row by row. And then our breaking point is going to be, we can actually pass in this n value here as well. if row equals n, if this row is 0 indexed, this will be, so n is 4 in this case. That means we've placed all the queens because we've passed the last row. So here we can just return 1 because we have a valid solution. Now we need to handle actually placing the queens. So for I in range, and then this is going to be, so this is an n by n matrix, so I can just do n. We need to iterate through every column and try to place a queen. So first we need to check, is this a valid square? So if, we're going to have a lot here, columns I, and these need to all be not, because it needs to not be in any of these. So if not columns I, and then we need to do an and, not, sorry, this needs to be like this. Okay. And then it needs to also not be in the left and the right diagonal, so left diag I, and not right diag I. So this means we are allowed to place it. So how do we place it? Well, we just simply mark all these locations as true. So we say columns I equals true, left diag I equals true, right diag I equals true. So now that we mark these as true, we're saying we placed it in this column and this left and right diagonal. So now what do we need to do? We need to backtrack to the next row. So if we're at row 0, we need to backtrack to row 1 and so on. So this would be row plus 1. N is the same. So now that we did the backtrack, we need to clean up. So after we backtrack, we need to remove our queen, which would mean we recurse back to where we put the queen. We need to remove it from here, and we need to try the next column. So how do we remove it? Well, easy. We just take these same things and we make them false. So I actually forgot one more thing. So we need to have some kind of variable to keep track of how many valid solutions we have, and then we need to update it here. And so every time we get to a valid solution, it will return 1, and we recurse back, and we will add another one to the res here. Then we simply return res here. And we need to call this function, so we can just say return backtrack. We start at row 0, this is n, and I think this is all the code we need. So let's try that. Let's see here. 2, 4, 24. Okay. So let's see what we did wrong. Oh, okay. Actually, no, that's fine. Return res. So let's think about this. Res plus equals backtrack row plus 1. Okay. Row equals n. So we're somehow not incrementing this res correctly. And I think that's because if we have a valid solution, but no, that should be fine. Res equals 0, return res. If row equals n, return 1, right? Okay. So if we recurse back up, what happens? That should be fine. O plus 1. So that is interesting that it's 24, but this is correct. Okay. The other thing we can do, actually, that would make it right for sure, is we can have it here. And now we can just do this. So I'm sure we could fix it in another way, but this would work 100%. So instead what we can do, null equal res, and then we can just update it here. So we're saying that once we get to a valid solution, we just update this res that's up here. I think this could work in another way, but we're just going to do this, and this should work for sure. $24. Oh, right. Okay, so that is, this should just be returned. This should be oh, actually, I know what I did wrong. Yeah. Okay, yeah. So I know what I did wrong. So this should not be I. So let's just change this. So this should be for column in this. So this is column, but if you remember, our left diagonal is actually column minus row. So this is column. So we're just, okay, and then this is column minus row. So that's what we did wrong. This is column plus row. But we can still leave the res the way it is. Okay, then here we go. So yeah, we shouldn't have had this I. This should have been like this. And now we do this as well. Left diag, right diag. Okay, let's try that real quick. And then we can return res here. Right. So this is column. Column. Okay. Okay. Well, let's try to submit. Yeah, so that's what we screwed up in. Okay, and I am curious, so let's just change it back to the way we had it, and I am curious if that'll work. I think it should now. So let's just try to do that. But yeah, this non-local one would work for sure. It's an easier way to, if you're not sure if you're adding up correctly, you could always have it out here, because that way you're not depending on the return value of a recursive function. You can just update it directly. But this should work as well, but let's just make sure. This will be a return. Yeah, okay, let's see. Okay, so now let's think about the time and space complexity for this problem. So time, space. Okay, so time. We are trying to place a queen in every single square, and then we keep recursing down. So if this is n by n, we're going to try to place a queen in. Backtracking is pretty much a brute force. So we're going to try to place every combination, so it should be n by n. Squared. And space. So let's think about space here. What is are we making any variables that hold things? Yes, we are. So we have these. And space-wise, so this column is n, this is n, this is n, and what else are we doing? So we have a backtrack. Now, what's our biggest recursive call stack? Well, it can only go down the number of rows. So if this is n, this is n, this is n, and this is n, that means our space complexity is 4n, which would just go down to n, because we can't, our biggest recursive call stack is only going to go down the rows. It's never going to have more than the number of rows. So I think the space should be O of n, and time should be n squared, because this is pretty much an nested for loop. Okay, and I think that's all for this problem, so I'll see you in the next one.